It's my pleasure to welcome to the Michigan MassTimber Community of Practice, Dr. Mojgan Nejad. She is a professor in the Department of Forestry at Michigan State University, and she's going to be presenting on her bio-based, lignin-based adhesives and coatings for mass timber. And Mojgan, I am so excited that you're here. I tell you all the time, and I tell everybody who I talk with about your work that what you're doing is one of the reasons I wanted to join MSU in the role of that I occupy with MassTimber at MSU. This work really has the opportunity to transform the adhesives that we're using and the coatings that we're using in mass timber to something bio-based and biodegradable and significantly lower carbon. So Mojgan, with that, I'm going to stop sharing my screen so that you can share yours. And then I welcome you to the Michigan MassTimber Community of Practice and to begin your presentation.
Thank you so much for having me, Sandra. I really appreciate this opportunity. I'm just going to start by saying that my entire presentation is focused on adhesives. I wasn't planning for the coatings. I have one pictures on coatings that I added as you were doing the introductions, but I'll be more than happy to have another entire presentation focused on coatings because we have a ton of data on the coatings too. Again, thanks for having me. As Sandra mentions, I am associate professor at the Michigan State University. I have a joint appointment in Department of Forestry and Department of Chemical Engineering and Materials Science. Today, I'm going to focus on lignin-based polyurethanes adhesives. Just to give you an overview of type of adhesives commonly used in mass timbers, one of the most common ones is the polyurethanes. It could be one component or two component adhesives. With one component means everything is in one batch. With the two components means it comes into different, like two different components. Sometimes is one of them is polyols, the other one isocyanate, that they are mixed together before application. There's also a formulation is called emulsions polymers isocyanate, EPI. This is basically polyurethanes similar to the first one, but they are basically dispersed or emulsified in water. And the common name that you might have seen it is isocet. The other one is phenol resorcinol formaldehyde, and I've seen a few mass timber producers are using that, but it's not as common as polyurethanes because they're a little bit concerned about formaldehyde that is in this phenol formaldehyde adhesives, and most mass timbers industry, they're not designed to be able to capture if there's any formaldehyde release, and as it's not as safe for the people who are working in the mass timber production. And then when we are talking about polyurethanes, in general, they're made of two main components, isocyanates and polyols, that they react together to form these urethane linkages, that they are very durable linkages. Polyurethanes used for adhesives can be used for coatings, especially wood coatings in high traffic area. It's used for making rigid foam, flexible foams, elastomers, has a ton of application. All of them are these main chemistry. In terms of phenol formaldehyde, we have phenol and formaldehyde that they're reacting together. After curing, we're going to see this methylene linkages. Is a very durable adhesives, water resistance too, but mostly used for plywood or oriented strand board, OSB application, not so much for mass timber. Some of you might have heard that when they're using polyurethanes adhesives in mass timber application, they usually call it moisture cure. The way they're calling that moisture cure is come back to these structures. I mentioned that isocyanate is going to react with polyols to form these urethane linkages. But when they apply the adhesives on wood, usually they require some level of moisture in the wood. And then the excess isocyanate that is there also is going to react with the moisture in the wood and forming this unstable carbonic acid that is going to either cure the amide groups and CO2 that is going to be released or create urethane linkages and which basically and then CO2. The foamings that you see in mass timbers after the production, you see some foams on the side is because of this reaction of isocyanate with water that is happening. Now let's look at why lignin, why I'm focusing on lignin. Main reason is because lignin is the second most abundant natural polymers after cellulose in the world. Any plants or tree you see, there's going to be a 15 to 35% of the dry mass of that plant is made of lignin. Lignin is a natural glue in the wood that keeps the cellulose fibers together. How is it produced? Currently, pulp and paper industry, when they start with the wood or biomass, they go through the chemical isolations, remove the lignin, and use the cellulose fibers to make paper and paper products. And then lignins, along with hemicellulose, usually end up in the black liquor that most of the time they just burn it to create energy, but some industries start thinking about instead of burning lignin as a source of energy, they can isolate lignin and use it for making higher value products than just energy in it. Also, biorefineries that they basically use biomass, usually agricultural residue, to make bioethanol for biofuel productions. They have lignin that is left over that we could use that lignin that currently is considered as underutilized portion of biomass for creating, again, these high value products. Another benefit of using lignin, because it has aromatic structure, is has antimicrobial, antibacterial, and flame retardant properties. And lignin comes from the plant, is renewable, biodegradable, and overall has a cost effectiveness depending on whether we're going to use lignin in its unmodified shapes or through which processes goes. But overall, it is a natural polymers and can be available in significantly lower cost than synthetic polymers. As you know, like based on different wood species, you're gonna see like even though all of them we call them wood, they have different properties, physical, chemical properties, appearance is different. The same applies to lignin. If you get the lignins from hardwood species or softwoods or agricultural residue, or even the process that is used to isolate lignin from the biomass is going to change the structural properties of the lignin. These are 40 lignin samples that you can see. They come in different color. It's not just the color, the properties are different. That's why whenever we receive a lignin samples, we fully measure their properties, chemical, physical, thermal properties to understand the parameters or properties of the lignin. And based on those properties, we decide this lignin is good for this application or better for this application than others application. Now I'm going to talk about the lignin-based polyurethane adhesives that we produce at MSU and scaling up through our new startup. The lignin-based polyurethane adhesives that we developed, we did it by replacing 100% of the petroleum-based polyol, which is one of the main components of the polyurethane adhesives, with our patented technology, as we call it, liquid lignin polyol. Because it's in liquid shape, it makes it much more easier to use it in manufacturing facility and mix it with polymeric MDI as a second component to make these adhesives. As I mentioned, polyurethane adhesives, some of them are one component, some of them are two components. In this, at this point, we are focusing on two component adhesives. One of them are liquid lignin polyol, and the other ones is polymeric isocyanate, which is one of the safest aromatic isocyanate that we could use compared to the other types of isocyanate. The formulation that we have has more than 30% lignin on the weight basis, and this was designed to be cured at room temperature, similar to the commercial adhesives, and is designed for mass timber applications as a structural adhesives. When we prepare the samples, we need to test it both what they call it for dry adhesion strengths and wet adhesion strengths. Based on the ASTM requirements is that after we make the CLT samples, we need to wait 7 to 8 days, almost 1 week, before we can measure the adhesion performance. This is a time for adhesive to be fully cured. And then in wet adhesion is very rigorous testing. What they require is that we make this CLT sample similar to these samples that you see in this picture. We have to soak it into the boiling water for 6 hours and then immediately remove it and put it in the cold water for 2 hours and test the adhesions right away after the cold water testing. Even though there is a very strict requirement for test samples that we are preparing, this size is 15 centimeters by 2 centimeters, but they also care about the grain orientation of the wood. Has to be between 30° to 85° the grain orientations. That's the angle that we need to use. The difference between lignin-based adhesives versus commercial adhesives, lignin-based adhesive is a dark color. And when we apply adhesives, you're going to see a very thin black color in it. But the commercial adhesives, even though it looks yellow here when it's applied, it is transparent. That could be one drawback for some applications. But when I show the samples to many architects and construction management, they all say that's not going to be a limiting factor for using that because the adhesives layer is very thin, and sometimes if they don't apply the adhesives to the edge, you don't even see that dark color. After we make these samples, we are using instrument machines to measure the adhesives strength of the samples. You can see the force applied, and when that happens, we call them adhesives failure. This is not the lignin-based adhesives samples, but what we usually like to see is that the force is strong enough that cause the wood to fail rather than adhesives failure. And this is the samples. You can see that this is a commercial adhesives. And then these two are made with the craft softwood adhesives and organosol with straw adhesives that we make. When that happens, you can see that the failure happens on the wood rather than adhesives. And this is what we call them 100% wood failure. And this is the criteria that we do. Not only we measure the adhesion strength, but we also look at percent wood failure, both in dry and wet tests. This is an example of the CLT samples that we made with the lignin-based adhesives. You can see that very thin black color, and that shows we use lignin-based adhesives. When we look at this data, the ones on the left are dry adhesion tests, and the blue ones are the wet adhesion tests. The first one is the lignin-based adhesives we made with the craft softwood lignin. And then the middle one is with the organosol with straw lignin. And then the last one is hydrolysis hardwood lignin based adhesives. And the final is the commercial one component polyurethanes adhesives. Based on the requirement, the dry adhesion should be above 10 megapascal. And then the wet should be, this should be around like above 5 megapascals. And you can see that all the lignin-based adhesives met the standard requirement, and they're actually outperforming the commercial adhesives. Because there was some discussion around, the previous data that I showed you is all on the softwood. We got those samples from spruce, pine, fir, a mixture of these softwoods from Canada. But in Michigan, we are trying really hard to get some of the CLT producers come and build a manufacturing line in Michigan. And we have a lot of hardwood in Michigan, and we wanted to know if our lignin-based adhesives works on hardwood species too. We tried soft maple, aspen, and poplar. Poplar, we get better performance, but these are not, we haven't even optimized our formulations for this. We can tweak our formulation and get even much better result for soft maples and aspen. Sorry. Okay. And then what we also, I was getting questions from automotive producers and others, can we use these bio-based adhesives for like bonding plastics or aluminum metals together. That's why we tested for high-density polyethylene plastics and aluminum plate. We got really good result for two plastics and metals too for some application. Again, for automotives application, this could also be used as a bio-based adhesives for them too. The other questions that we had as we were talking to one of our industrial partners, they were interested in using heat-treated woods. For those of you who don't know what is heat-treated wood, they basically use like either steams or oil to cook the wood, like similar to what you make, how you make French fries, that it shouldn't be oxygen for environment or steams. They put that wood into around temperatures between 180 degrees C to 220 degrees C. During this heat treatment, there is no chemical involved, just the heat treatment. What happens, we see some chemical modification of the wood surface. After heat treatments, the wood, doesn't matter which species it is, some of them works better than the others, but all of them become more dimensionally stable. And because of these changes in hemicelluloses that we see on the wood after heat treatment happens, we're gonna see some improvements in performance of this heat-treated wood. I have to some degree a resistance to decay and also insect attack. And this dimensional stability makes these samples better for exterior application if we want to use that for those exterior applications. After heat treatments, because this modification happened, they reduce the surface, they change the surface energy of the wood. We have always problem with adhesion of different adhesives or coatings to the heat treated wood. We want to test it. We had different samples that heat treated soft maples, red oak, ash, and pine that was provided to us. And we tested our lignin-based adhesives versus commercial Henkel adhesives. What we found that with our adhesives, again, without optimization, has better performance, better adhesion strength on heat-treated wood compared to the commercial adhesives that we have. Sorry, and there's a typo here. I didn't notice. My apology. Another test that is extremely rigorous, and they only do that for a structure of adhesives. They usually don't do that for plywood or OSB or other products, but for MassTimber, it is designed to do that. Now, basically, you put these samples in autoclave in vacuum applications in really high pressure and vacuum that is applied. And based on the EN 302 test, we have to do 2 cycles. The first, the cycle starts with vacuum pressure on 25 kilopascals for 15 minutes. And then after that, applying pressure 0.6 megapascal for 1 hour. This is the first cycles. And then we're going to do another second cycle, again, repeating this. And after that, we're going to put that into the oven at 65 degrees C for 20 hours to fully dry. After that happens, what we do usually, we look at the delamination. The delamination is basically delamination all around the area of the adhesives that we have, like for example, these sections that we are seeing. These are samples before the delamination test. This is after. And we measured the area after first cycle and after second cycle. After first cycle, this is craft softwood adhesives, organic salt, hydrolysis, lignin-based or lignin-based CLT samples made with the lignin-based adhesives. And then this is the second cycle. Anything that below 10% is acceptable by standards. The craft softwood delamination was higher, but still lower than the commercial adhesives. And then the 2 organosolvent hydrolysis softwood has very, very low delaminations that we see in these samples. All of them are acceptable, but this is another, again, really rigorous test that needs to be done and shows that how strong these adhesives are. We collaborated with Forest Product Lab. Our colleagues, Laura Hansberg, did this fire performance test for us in Forest Product Lab. This is based on ASTM E1355 cone colorimeter test that the samples are basically put into cone colorimeters. We tested again 3 lignin-based adhesives and the commercial adhesives. What you see here is basically heat release rate, representing that like the heat energy that is going to be released as we are burning the CLT samples per the unit area. At the beginning and end of the peaks is basically the ones that the heat release starts from the air to the wood, and at the end from wood to the air. And in betweens are the CLT samples. With all the lignin-based CLT samples, with the lignin-based polyurethane adhesives, it's just basically almost a straight line along the way. But in the commercial adhesives, we see 2 major peaks in here and there, and that as we are talking about. This heat release, like increase in the heat release that we are seeing, happens through the bond line. Now, this is a 3-ply CLT, small CLT samples. The first glue line, bond line, and the second one. And this is indications that when it gets to this polyurethane adhesives, commercial adhesives, we see some burning of the adhesives and generating heat, and that comes from the adhesives in the second line too. But the lignin-based adhesives, because of the aromatic structure of lignin that we have, they create the char and prevent this like burning of adhesives and generating heat that happens. And these are the samples that we sent to Forest Product Lab. These are before testing. This one made with the commercial adhesives. And you can see that the clear adhesives and the other ones are the samples that we made with the craft softwood, organosol, and hydrolysis hardwood adhesives. These are the samples after the test. You can see that the ones with the lignin-based adhesives, even though it's fully burned, but the steel adhesives was strong enough to keep them together. And the commercial adhesives samples, as soon as they opened up, it completely fell apart. We knew that is going to happen because lignin is a natural flame retardant, but seeing this performance was very encouraging. Seeing that this is bio-based adhesives and has really good fire performance or flame resistance. Another questions that we usually get from CLT producers is that, like these adhesives that you're providing, does it have enough low viscosity that could be easily applied by a spray application? And that's why we tested. We tested that. We found that these are just lignin-based adhesives. As we are increasing the temperature, like for example, at around like 5 degrees C up to like 30 degrees C, we see significant drop in the viscosity of adhesives. This is the temperature that also recommended for commercial adhesives to warm it up to 30 degrees C. The viscosity is so low that can easily be applied. We also look at the viscosity change by shear, because this is the 2 component. We need to mix them together. As we are mixing them together, this is a very low shear rate. Then you can see that even around like 400, 500 RPM, we saw a significant drop in the viscosity. Again, make it very easy to be applied through a spray application. Now let's try to compare this lignin-based 2-component adhesives with the commercial 1-component polyurethane adhesives. I mentioned some of the industry MassTimber producers that are still using 2-component polyurethanes too, but this is based on the 1-component that we compared in this study. For the commercial polyurethane adhesives, usually recommended that CLT producers sand or plane the wood samples that they're gonna use within 24 hours, like basically freshly sanded samples. We tested our adhesives even with the samples that was plain or sanded 3 months ago. We still got good result. Therefore, we don't need to freshly sanded wood. They also, because it's a moisture cure adhesives, they usually recommend that the wood should have higher moisture content. That's why they recommend to spray water before pressing the samples. What we found out there are adhesives, because the amount of free isocyanate is low, is a two component that they're mixing together. It's not as sensitive to the moisture requirements. We only recommend that spraying water if it's been very, very low moisture content, below 5% or so, which doesn't usually happen. And then for the 2K adhesives, again, some formulation, they recommend that you apply primer. And what we don't need primer applications for the lignin-based adhesives. The difference is that for one component adhesives, just one component, there is no mixing requirement. But for our adhesives, because it's a two component, they should have a mixer at the beginning to mix the two components together. The recommendation is that, like usually in winter time, especially, you need to warm it up slightly above room temperature to 30 degrees C. And this is also help our lignin-based adhesives, because as I showed, it's gonna drop the viscosity, make it easier to spray it. Gelation time or open time is that when you open up the adhesives or mix them together, this is a time that you have before the adhesives become gels and you need to apply. The commercial adhesives and the one component, we measured the gelation time was around 45 minutes. It could be different formulation that they have higher open time. And our adhesives, we have something around 20 to 30 minutes open time. With the commercial adhesives, as I mentioned, when they react the adhesives with the moisture in the wood, it ends up having some foaming on the side of the CLT samples that needs to be removed. We didn't observe this foaming with the lignin-based polyurethane adhesives. We also hired an outside firm, and they did a LCA life cycle assessment for our liquid lignin polyol, which is the main component we are replacing with the petrochemicals polyol. What they found, because we are using lignin that has bio-based carbon in it, we're going to end up having negative net zero carbon for our raw materials. We are using a little bit of energy that we are using. There's going to be some small emission, CO2 emission that is going to come. The plants and equipments that is used almost zero increase in the CO2 emissions. Transportations, if they make the adhesive to transport it to the CLT production, we're going to use some energy for that. But if they combine all of you can see that we are basically negative. We are still the CO2 emissions, because we are using a bio-based materials, is carbon negative. The lignin-based polyol is carbon negative. And what we actually did a manufacturing trial on the Element 5 site in collaborations with Henkel. We went there and we made larger scale glue lamp samples. After the sample were pressed, they cut the samples in half, sent half to Henkel, half to MSU. We tested all those samples that was prepared for delamination. And even though, like, the people who were applying adhesives, none of us were expert on application of adhesives, but the glue lamp samples that we made passed the delamination and other tests that we've done. What I call it, to summarize, this lignin-based adhesives is going to go beyond just being the sustainability. As I showed, the lignin-based polyurethane adhesives have better dry and wet adhesion performance compared to the petroleum-based conventional one-component polyurethane adhesives. It also had a really good adhesions to softwoods, hardwoods, and heat-treated woods. The CLT that we made the CLT samples that we prepared with the lignin-based polyurethane adhesives had significantly better fire performance than the commercial adhesives. What we found through the life cycle assessment that using liquid lignin polyol instead of fossil fuel-based polyol that is used to make polyurethane adhesives is going to reduce the CO2 emission by 81%. And again, my apology, I thought I'm going to focus on adhesives. This is one of the study that we tested 35 commercially available coatings for mass timber application. I'll be happy to have another lectures that I'm going to focus on the coatings, wood coatings in general, and mass timber coatings that hopefully next time, if there is opportunity, I'd be delighted to come to another of these meetings and talk about wood coatings. I want to thank all the funding agency and industry partners who supported our projects. I have a 4 years USDA NEFA funded projects, and in these projects, we're going to collaborate closely with Forest Product Lab and Sterling's to scale up production of our lignin-based adhesives to a 5-gallon scales and take it to the manufacturing line of Sterling's and make a large CLT samples there. Thank you so much again for this opportunity. This is my email address and phone numbers. If you have any questions, I'd be more than happy to answer any questions you may have. Thanks again.